Hey guys, this lesson is about finding the volume and surface area of something called a frustum. A frustum is the portion of a cone or pyramid which remains after its upper part has been cut off by a plane parallel to its base, or which is intercepted by two such planes. So basically, you have a cone. Now, we have this cone drawn out and labeled for us right here. However, along comes this plane that chops off the small cone from the top, or smaller cone, and now this is called a conical frustum. We have a circle on top and a circle on bottom, so one of these circles will have a smaller radius. You can either call it R1 and the larger radius R2, or sometimes what I like to do is use a lowercase r for the smaller radius and a capital R for my bigger radius. Now this H, it is kind of nice to switch it up to a capital H. As you see here, they use lowercase h. Lowercase h really represents the height of the entire cone before it gets chopped. Here, what we have, it's a little hard to count, but we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 vertices. So this was a decagon-based pyramid. So we have a decagon as the base, and then the top was chopped off. So this is a decagonal pyramid frustum. Here's another conical one, just looking at a couple different pieces. We have our height labeled here. They used a lowercase h in this picture and the lowercase r and capital R like I recommended. And here they're calling this distance L. So you might see this distance called L. You might see this distance called capital S or lowercase s, sort of like the slant height. So it will vary from book to book, teacher to teacher. It really, it doesn't matter what you call it as long as you know what's going on. Here we have a couple other pictures that I've included that I just added to this worksheet here. Here it kind of shows more the progression of using a plane to cut it off and being left with this right over here. And again, this time we have a hexagon-based pyramid. And I would guess that this would be like a regular hexagon, meaning all sides and angles are congruent, but that isn't always the case. Now, another picture that's kind of cool to look at here is this over here is, right here, this is a sector. If I keep going around, we'll make a whole entire circle. So this is a sector of a circle, and some angle up here tells us what amount of 360 degrees are we looking at. If you roll up this little sector, you make a cone. This is where cones come from. If you watch the cone volume and surface area video, I actually did make one. And if you kind of pause and pay attention to what I did, I really break down how this angle can be determined based on what you want your height and radius of your cone to be. So a conical frustum will have more of a pizza crust, more than just like a segment. You learned about segments, or the straight line connecting from there to there. That was kind of like an idea of a pizza crust. This is a little bit more legit pizza crust, but rolled up into a bit of a lampshade looking visual. So here, this is radius 1 and radius 2. The radii, again, you could see this in the cone video where I showed you how I built a little paper cone myself. The circumference around here is actually the arc length right there. And the circumference around here is the arc length right there. If you remember the formula for arc length, it was, and remember it's a fraction of circumference, where theta is the angle up here. So sometimes you're going to know the radius and you're going to know what that arc length is. So I'll call it AL for arc length because I was using S before and now we have slant height. I don't want to confuse people. You might know the arc length, you might know the radius and have to figure out the angle. So you just solve differently. That's all. You just isolate a different variable. So I have a few examples of the volume and surface area of conical frustums, and I'm going to do a couple of them with you right now so we can really derive a formula together. Now, if you were to look up the volume and surface area formulas for a frustum, you would see the following formulas. Let's start with the surface area. So if you copy these down and have them in your notes, at least you'll have them written already, and then we can go over how they work and why. So your surface area formula might look something like this. Pi times the quantity of the larger radius minus the smaller radius times the square root of larger radius minus smaller radius squared plus h squared. And then your volume formula might look something like this. And I say might because sometimes people teach the volume and surface area a little bit differently. They might make it a little bit more like what I'm about to show you, where you kind of go on to your little journey and you find different bits and pieces, add, subtract, multiply. So we have pi over 3 times h times the quantity of r squared plus r squared, both of the radii, plus larger radius times smaller radius. So we're going to work through example 1 right here and see if we can understand where these formulas come from. But we're going to treat example 1, like I just mentioned, like we're doing a bigger cone and then a smaller cone and subtracting the difference and maybe like adding the top and bottom in. And well, we're going to really dissect this example right now. So let's go ahead and get started. So in this picture, like I mentioned, we have a few pieces of information labeled for us, but not everything. Something that's really important, a really big takeaway, is that this triangle in red right here is really going to represent from the apex right there down to the center of the bigger base and then out to the circumference of that larger base. And it has another triangle inside of it. Because they have this angle up top in common, and they both have a right angle, they have 2 angles congruent. That means they have 3 angles congruent. That means that they're similar triangles. If they're similar triangles, if I found the tangent of this angle in the smaller triangle, for example, opposite over adjacent, it would be the same as the tangent of the angle in the larger triangle, opposite over adjacent. The same with sine, opposite over hypotenuse for the little triangle is equal to opposite over hypotenuse for the larger triangle. Knowing that these ratios are congruent or are equal to each other rather, will help us find a lot of pieces that we might think are not known right now, but really we do have enough information to figure them out. So this triangle, if I were to revolve this triangle around this line right here, sweep it around, it would make the bigger cone. And if I only swept this one around this axis right here, it would only make the smaller cone. So if I wanted to find the surface area of each and sort of use those pieces to, or parts of the surface area to figure out the surface area of that, I can do that for sure. So what was the formula from your surface area of a cone, what is the formula for the lateral area on a cone? We're going to do lateral area of the big cone minus the lateral area of the little cone. So I'm going to use capital and lowercase letters for my abbreviation. The lateral area, and that's just part of it. This is not everything. We also have to do the circles. So this is phase one. The lateral area is pi s r, and then it's going to be minus pi s r. That s probably could be a little bigger, where s is the slant height. So that will get us this lampshade portion. So we have this plus the top circle, which is pi r squared, plus the bottom circle, which is pi r squared. So it's this plus each of these. Lampshade portion, top circle, bottom circle. Okay, now I have that this measurement is 1, I have 9, and I have 4. I don't have everything, but if I could figure out this piece right over here, which I'll call X, then I'll have 2 out of 3 sides in both right triangles, and I can solve for everything else that might be missing. Actually, right now, I don't even need these sides. I really just need this slant height on both of them. How can I figure this out? Well, the sine of theta. The sine of theta is equal to 1 over x. But the sine of theta is also equal to 4 over what? It's equal to 4 over x plus 9. Now, how can I go about solving for x? This is just a simple algebra problem. I can multiply both sides by x, and I can multiply both sides by x plus 9. X plus 9 times 1 is just x plus 9. 4 times x is 4x. Subtract x from both sides, and you'll have 9 equals 3x. Divide by 3, x equals 3. Nice. So 3 is the length right there. That means this whole entire slant is 3 plus 9, or 12. If I wanted to use Pythagorean theorem, I can, and that will get me this measure right here. And then I could do it again in the bigger triangle, it'll get me that measure right there. So if I were to use capital and lowercase letters, S would be the trickiest one because, well, a capital and lowercase s aren't too far from each other. But if I did, this would be little s, or you can maybe call it S1, and that's big S or S2. Here, this is lowercase r, or R1. This is capital R, or R2. 9 isn't really anything, remember that, but 3 is, right? 3 is the S1. Here, that's H, lowercase. This is H, capital. That means that this height in here is really capital H minus lowercase h, which will be important later. Now I'm going to use this formula to figure out my surface area. The surface area of my conical frustum is pi s. We're going to do the bigger one first, so we might call that S2. R, or maybe you just know it's a capital S because with the capital R, whatever you need to do, minus pi SR plus pi r squared for the top plus pi r squared for the bottom. Now let's fill in everything. We have 12 4 3 and 1 plus pi times 1 squared plus pi times 4 squared. 12 times 4 is 48 pi minus 3 pi plus 1 pi plus 16 pi. 48 plus 16 I know is 64 minus 3 is 61 plus 1 is 62 pi. So the surface area of the entire conical frustum here is equal to, I almost put the approximately, but this is in terms of pi, so we're precise, 62 pi. We don't have units, so we're just going to say units squared because it's an area. Now, let's look at how you would do the volume. The volume of a conical frustum is actually a little bit easier. You're going to do the volume of the larger cone minus the volume of the smaller cone. So this is the volume of the frustum. The larger cone, well, the volume of a cone is what? 1/3 area of the base, which is pi r squared, times the height, h. The larger cone, I'm going to use my capital letters, pi r squared times h minus 1/3 pi r squared h. Now, here it's a little easier to see that other formula if we factored out the 1/3, and if we factored out the pi, we'd have a pi over 3. We also have r squared minus r squared, so that should look like something somewhat important, but we're going to get into this a little bit more when we look back at our picture in a few minutes. So if we wanted to fill all of this in, we really do need these heights. In order to figure out those heights, I need to do the Pythagorean theorem. So I'll have 1 squared plus h squared equals 3 squared. 1 plus h squared is 9. H squared equals 8. That means that h equals the square root of 8, which is really 2 radical 2. So that's our lowercase h. For the larger one, there's a few ways that you could go about this. While you could do the Pythagorean theorem all over again, we did learn a trick when we first learned Pythagorean theorem that could prove quite helpful. Here, this leg is 1, this is 4. This leg is 3, or I'm sorry, hypotenuse is 3, and this is 12. What is the scale factor here? Each side of the smaller triangle is actually 1/4 of the size of the larger triangle, or we could say that the larger triangle is 4 times in length. The sides are 4 times longer than that of the shorter triangle. So that means capital H would actually equal what value? If it's 4 times bigger, it's going to equal 8 square root 2. All you need to do is multiply by 4. So capital H is 8 square root 2. big time saver. Then we could just fill in all of the pieces. 1/3 pi, I can factor out front, save it for the end. Capital R squared will be 4 squared, or 16, times capital H is 8 square root 2, minus, remember I factored that 1/3 pi out front, lowercase r is 1, squared is 1, which I don't really need to write, and lowercase h is 2 radical 2. 16 times 8 is the same as 16 times 2 times 2 times 2, because 8 is 2, 2, 2. 16 times 2, 32, times 2, 64, times 2, 128. So this is really 128 rad 2 minus 2 rad 2, which equals 126 radical 2 times that 1/3 pi out front. 126 actually does divide by 3 because the digits add to 9. 126 divided by 3 is 42. So that means the volume of the frustum is equal to 42 pi radical 2 units cubed. So we found the volume, and we also found the surface area. Here is the next example we're going to do. This time, instead of being given 3 measures, we're given 2 measures and an angle. The angle comes in really handy, of course, because 60 degrees allows us to use special right triangles to figure out other information. If this angle here is 60, then this angle here is 60 as well. We know both of those are 90, and they share this angle of 30 degrees right there. This right here is 3 radical 3. And down here, we have 4. 4 is actually capital R. And this right here is actually capital H minus lowercase h, if you label it the way I did before. Now I'm also going to go in and add some other pieces of information. Here we have lowercase s, or S1, and here we have capital S, or S2. This right here is lowercase h, oops, and this right there, whole thing is capital H. Across from the 30-degree angle, we have 4. That's side x. That makes this side x radical 3. So the height of the entire cone, if it were there, would be 4 radical 3. If this is 3 radical 3, this must be 1 radical 3, because that's all that's left to make 4 radical 3 altogether. Again, if this is x and this is x root 3, then this side is 2x. So this is 8. And if this is 1 root 3, then this side is 1. And this side is 2. And that 1 is really the lowercase r. This was actually even easier, even though having an angle might be a little bit intimidating. We really just found all of the key pieces of information that we needed to know. Now, if we go over our formulas again, we have surface area, which is pi times bigger radius minus smaller radius, times the square root of. Now, I didn't do it this way before. If you prefer doing it the way I did before, by finding the lateral area of both and subtracting, knock yourself out. Personally, I prefer that way because to me, it makes more sense. I'm writing this down because you do have the option to be a formula person and follow the formula. If we have time one day, we will go over the full derivation of exactly how this gets constructed the way it is, but it takes a bit of time. So I'd rather just get to practicing for right now. volume is pi over 3, or 1/3 pi, times small h, or lowercase h, r squared plus r times r. But like I said, it's up to you how you want to go about doing this. I'm just going to slide this. Let's go kind of like that. So we're going to do, let's do the volume first this time. That's going to be 1/3 pi. They both have that. I'm going to leave that factored out. So then I'm left with r squared h minus r squared h. 1/3 pi. Large R was 4 squared times h, which is 4√3. Minus small r is 1 squared times h, which is √3. 16 times 4 is 64. 64√3. Minus 1 squared is 1. 1 times 1√3 is √3. That simplifies to 63√3. So then we have 1/3 pi of 63√3. 3 divides into 63 evenly, so we have 21 pi radical 3 for the volume of the frustum, units cubed, of course. There we go. As for surface area, we have the top circle, which is pi 1 squared. We have the bottom circle, which is pi 4 squared, plus we have SR pi of the bigger one minus SR pi, or pi SR, whichever way you write it, of the smaller one. S of the larger was 8, smaller was 2, so we have 8 times 4 pi minus, and then we just said we had 2 times 1 pi. 1 and 16 is 17 pi. 32, take away 2 is 30. 17 plus 30 equals 47 pi units. I'm going to use u squared, and there I just used u, same idea. So there's 2 examples, and then I have 4 others for you to try. So I hope that you can follow. If not, I'll try to post some more support videos going over this, and I'll try to put together a video if I have a chance going over where these formulas came from. But definitely rewind, look at how I came up with those equations, and give the other 2 examples on each of these pages a try. So there's 4 examples. Good luck!